All right, welcome back to our third stats lesson. And today we are going to be looking at normal probability distribution. It is one of the longer lessons for this unit, so sit back and enjoy it. So let's take a look at the definition of what a normal distribution is. It says it is one of the most important probability distributions. It has been discovered that many observations of physical measurements such as length, volume, mass, and time, etc., all have common characteristics in how their data is distributed. And we called this shape the bell curve or the normal curve. Okay, so this is very important because, like it says, this kind of distribution describes many physical phenomena. Okay, so it's very useful. Okay, let's look at this first example here. It says a manufacturer who makes 100 watts light bulbs is interested in determining the distribution of lifetimes of the bulbs. After testing 44 bulbs, he calculated the mean life of the bulbs to be approximately 900 hours and the standard deviation to be approximately 50 hours. The lifetimes in hours of the 44 bulbs is shown below here. So here is the table that shows the lifetime of these bulbs, and we are going to convert this into this following table here. So we're looking at, we're going to count how many light bulbs are less than 800 hours. That's one of them, I guess, and this will be 1 out of 44, and if you put this into a calculator, this is 2.27%. Okay, 2.27%. So go ahead and finish the rest of the table. Okay, so if you complete it, this is what you should get. You can see this is symmetrical, right? You got 1, 6, 15, and then 15, 6, 1. So it's a nice curve. And this curve really is shown in part C right here. Okay, so this is what we call a normal curve. While we're looking at it, might as well finish filling out this distribution curve. Okay, so this, you can see this will represent 34.09% of the data. So that's talking about this region right here. This is 34.09%. So that is between that is the light bulbs will last between 850 hours and 900 hours. So that part of the curve represent the probability. Okay, 34.09%. Okay, this would be 13.63 repeating percent. That's 2.27%. Same thing here, 13.63 repeating percentage, and then 2.27%. Okay, so again, each part of the region, I guess, each region represents the area of which the probability of that, the light bulbs will last between those hours will happen. Okay, so that represents the probability. Okay, so let's go back to part B, and then it says using mu equal to 900, that's the mean, and sigma equal to 50, that's the standard deviation of 50 hours. Write the following numbers and intervals in terms of mu and sigma. So how do we represent 950 using mu and sigma? Well, 950 is simply equal to mean, right? 900 plus 1 standard deviation, sigma, 50. Okay, 800 then, well, we can write this as mu minus 2 times sigma, right? 2 times 50 is 100, so 900 minus 100 is 800. For 975, we can do something similar. So this is going to be mu plus 75 is not a full multiple of 50, but it is 1.5 times 50. That gives you 75. So this is 1.5 times sigma. And if you want to write an interval for 900 to 1000, well, this is going to be between, let's say we have 900 is going to be mu, I guess 2 mu plus 2 times sigma, right? So that's an interval from mu to mu plus 2 sigma. Okay, that will give you 1000. Okay. Okay, so that's part B. This is going to be important when we look at the questions later on. Okay, part C, anyway, let's go back to this. So this is the normal curve that we just graphed. That's what a normal curve looks like. And in the bottom here it says, this is a good approximation for the standard normal distribution curve. Okay, so this is the standard normal distribution. Now, when we draw graphs for like these situations, sometimes it might not be exactly, okay, so but they will be relatively speaking close to a normal curve, okay, and we can approximate it using normal curve. Anyway, I don't think we'll deal with that this. Actually, yes, we'll be looking at that at the end of the unit, okay? But not right now, okay? Right now, everything is just perfect, okay? Perfect. Standard normal distribution curve. Everything is just perfect. So here it says we would have, and again, it makes sense to have different means and different standard deviation for different data, right? Obviously, mean will be different, standard deviation will be different for different situations. Now, in order to compare normal curves and to solve probability problems involving normal distributions, we convert normal distribution curve into the standard normal distribution curve, okay? So here you can see this is where the mean is, okay? And the mean is, what is it again? 900, right? This is 900. And this is one standard deviation away, so this is actually 950. And this is 2 standard deviation away, so that's 1000. This would be 3 standard deviation away, that'll be 1050. So you can see it's unlikely, you can see this area is kind of small, right? It's unlikely that there's a light bulb that will last more than 1050 hours. Okay, that's just not likely. This is one standard deviation away from the mean to the left. So it's actually less than 900, right? So this is going to be 50 less, so that is 850. This is 2 standard deviation less than the mean, so that's 800. This is 2 standard deviation less, 3 standard deviation less than the mean, which is at 750. And you can see the area there is quite small. So again, that means it's quite unlikely that a random selected bulb will last less than 750 hours. Okay, so that's how this works. But then again, as we read it here, every single time when we have a different situation, the mean, the standard deviation is going to change. So we can actually convert into a standard normal distribution curve, like this one here, where you can see the mean is at 0 and, well, the standard deviation is 1. Okay, the mean is 0, standard deviation 1. So when you're 2 standard deviation away, well, it's at 2, and so on. Okay, so here are some key facts. The first one, again, like I just mentioned, mean is always 0 and standard deviation is 1. Okay, so it's nice and easy, right? 0, 1, 2, 3, negative 1, negative 2, negative 3. The total area under the curve is always 1. And again, that means this represents the probability, right? That makes sense. If you add up all the possibilities, the maximum is 1, right? So the total area under the curve is 1. And this is symmetrical, okay? So let's take a look. So from 0 to 1, this is 1 standard deviation. And you can see this actually accounts for 34.13% of all the data. And to the left, same thing, it's 34.13%. So really within 1 standard deviation. So when we talk about within 1 standard deviation, we're talking about to the right and to the left, right? So we're talking about the entire area right here. This accounts for 68.26%. It covers like pretty much everything. Okay, well, I shouldn't say everything. More than 2/3, right? Within 1 standard deviation of a normal distribution curve, it would actually cover 68.26% of all the data values. Okay, so that's within 1 standard deviation, which covers, we can say, most. Okay, so this is within 1 standard deviation, within 1 sigma. Okay, you can do the same thing and calculate what percentage it covers within 2 sigma, within 3 sigma. Okay, so I'll let you do it. You know what? I'll do it. Okay, so all we really need to do is just add up these numbers here. So we got 13.59. So 2 standard deviation then would be this portion then, right? So it's the blue part plus the extra red. So that's 13.59, and there's two of them added to 68.26. This is actually 95.44%. So within 2 standard deviation, it pretty much covers everything. And if we add the third standard deviation, I guess, if we account 3 standard deviations, so within 3 standard deviation, it's pretty close to like everything. We need to add another 4.3%, I guess. So if we add another 4.3, we get 99.74%. 99.74%. So within 3 standard deviation, it covers pretty much all the possibilities. It's unlikely that our data will be outside of 3 standard deviation. Okay. All right. That's the standard normal distribution curve. Okay, so let's take a look at this example, next example 2 here. It says a nurse records the number of hours an infant sleep during a day. He then records the data on a normal distribution curve shown below. The value shown on the horizontal axis differ by 1 standard deviation. Okay, so this is the mean, right? That's the mean. This is 1 standard deviation away from the mean. That's also 1 standard deviation away from the mean. So it says part A, what is the mean of the data? The mean, so mu, is 12. Part B, what is the standard deviation? The standard deviation here is 2. Okay, because you see from 12 to 14, right? The standard deviation is 2. What are the values for A, B, C, and D? Well then, in this case, well, because each standard deviation is 2, so I'm going to start with C here. This is going to be 16, right? And you just add another 2, that'll be 18. Same thing for B, we're going backwards, so you minus 2, that'll be 8, and minus 2, that'll be 6. Okay, I'll write it beside it so it's easier to see. Okay, D is as what percentage of a day does the infant sleep between 12 and 14 hours? So we're looking at this area. Okay, so this would be approximately, if you look at this, it will be approximately 34.13%. Okay, based on our standard normal curve. Okay, that is approximately 34.13% because we're looking at this region right here. Okay, part E says what percentage of a day does an infant sleep between 8 and 14 hours? So then in this case, we are looking at 8 to 14, so we're looking at this area. Okay, so if you again go back to the top, we're looking at within 1 standard deviation is 60.26, and we just need to add another 13.59, so 68.26 plus, what was it again, 13.59. This will give us, I have no idea, let me pull out the calculator. This is 81.85, 81.85%. Okay. Okay, F, it says, is it possible to figure out what percentage of a day that the infant sleeps for less than 13 hours? Well, 13 hours will be somewhere here in the middle, right? It will be right there. So, well, if that's all we know, then we can't, right? We can't really, I mean, I guess we can estimate, but we can't really figure out right now. However, of course, if I ask you this question, the answer has to be yes. I mean, otherwise, what's the point, right? It is definitely possible. We just don't have the tools yet. And so what we actually need is we need to introduce Z-scores. Okay, so what is a Z-score? Okay, it says Z-score describes the number of standard deviations above or below the mean. Okay, well, that makes sense, right? So Z-score is, so it's like, if Z-score, let's say, is 1.3, it means we're looking at 1.3 standard deviation above the mean. Okay, the Z-score could be like negative 2.5. It means that we're looking at negative 2.5 standard deviation away from mean to the left or below the mean. Okay, so that's what Z-score is. Z-score describes how many standard deviation away from the mean, whether it's above or below. So that depends whether it's positive or negative. So here is how you calculate the z-score. Z is equal to x, which is the data value, okay, a particular data value, minus the mean divided by the standard deviation, okay? So let's use this particular example that we just did, I guess. It says 16 would have been z-score of 2 because it is 2 standard deviation away. Okay, so and if you use this formula, it makes sense. So you see, z is equal to, so the x value, so this x is the data value, and we're looking at 16. 16 minus the mean, which is 12, divided by the standard deviation of 2. And you can see this is 4 divided by 2, which is 2. And it makes sense, you can see 16, this is 2 standard deviation away. Okay, so going back to f, I guess, or not going back yet, is the question here is what is the z-score for data value of 13? Okay, so for 13, the z-score then is going to be 13 minus 12, that's the mean, divided by sigma, which is 2. This is 1 out of 2, or 0.5. Okay, so the z-score for 13 hours will be 0.5. Okay, so we kind of standardize it, right? This is this, because you can see standard normal curve is 0, 1, 2, 3, negative 1, negative, negative 3. So we standardize this 13, this data value, to 0.5. That's the z-score. We standardize it. That's 0.5. That's the z-score. Now, what's the usefulness of this number, right? How am I going to use this number? How does this help me to solve this question? Okay, so then I guess what we're gonna do now is, you know what? I'm gonna hold it off for now. Okay, so we'll come back to it later. Let's be familiar with this formula first before we actually enter that question. Okay, so example 3 is as Jimmy's test marks are shown below together with the class mean and standard deviation for each subject. By calculating z-scores, determine in which subject Jimmy performed best relative to the rest of the class. So one way to compare how he does, or how he did compared to the class, is looking at his z-score, right? Because we want to see how far away he is relative to the mean. Okay, so it's not just about the score, it's about how he does relative to the class. Okay, so what we can do is to find the z-score for each of his mark. Okay, so for math, again, using the formula, it's going to be his score minus the mean divided by the standard deviation. Okay, and I'm just going to set it up so I can do all the calculation at once. The z-score for chemistry is going to be, so he scored 79 minus the mean divided by the standard deviation of 14. And the z-score for physics, this is going to be his score minus the mean divided by the sigma, 11. Okay, so this is actually 6 out of 12. Okay, that's easy to calculate, 0.5. This one is 6 out of 14. Not an easy number to calculate, so I'm going to use a calculator here. This is 0.43. I'm rounding to 2 decimal places. Okay, what the heck is this? 68 minus 68. 68 minus 66. I should have put 1 mark below the mean to see the negative z-score. Oh well, too bad. 2 out of 11 is 0.18 repeating. Okay. 0.18181818. So these are the z-scores. So I guess in this case, you would say this is the best score. Right? He performed the best because he is further away positively from the mean, which means he is away from the clutter, the most scores. So he did better than the average, I suppose. Okay, whereas this is really close to the mean, which means he is, he is kind of the average of the class. Okay, so the further away to the right is better, right? Further away to the left is worse. So if the z-score was negative, that means it did not do so well, okay, compared to the class. Okay, example 4, the marks on a math test in Mr. H's class were found to have a mean of 52 with a standard deviation of 12. Professor, okay, thought this exam was too difficult. He looked at my class and he thought this is too difficult. Okay, the stats professor came in and said that I'm gonna change the how the test is perceived, I guess. He decided to adjust the original marks by raising the mean to 65. Okay, so the mean is now going to be 65 while reducing the standard deviation to 10. Okay, and he's going to leave the Z-score unchanged. So what would the new mark be for a student who received an original mark of 34? By the way, I would usually don't scale. Okay, this is what they call it, scaled up grades, right? But I usually don't do it. But the professor stepped in. Okay, he said that's enough. Okay, so how do we do this? Well, since the Z-score is going to be unchanged, so what I'm going to do is I'm going to calculate the Z-score first for the original mark of 34. So to calculate Z, again, it's the score minus the mean. The mean was 52 divided by the standard deviation of 12. Okay, so this was the Z-score. So this is going to be negative 18 out of 12, which is negative 1.5. So this was the student's Z-score. Now, the professor decided to change the mean to 65 while reduce the standard deviation to 10. Okay, so not the new Z-score. The Z-score remains the same, negative 1.5. However, we don't know the student's new score now, okay? But we know that the mean is now going to be 65, so x minus 65, and the standard deviation is now only 10, okay? So we now can actually calculate this student's new score by solving for x, because remember, x is the score of the student. So if you solve this algebraically, you should get negative 15 is equal to x minus 65. And by adding 65 to both sides, you get x is equal to 50. So this student is now passing. Okay. So it was 34. Now this student is, the new mark for this student is now 50. Okay. And again, because we can do this because we left Z-score unchanged, which makes sense because we don't want to change how this student does relative to the class, because it's still the same test. So relatively speaking, this student shouldn't change the standing, right? It should be the same place. So we shouldn't change the Z-score. So we can actually scale the marks this way. Okay. All right. So these are about Z-scores. But we did all of these, but we still haven't answered this question yet. Is it possible to figure out what percentage of a day does infant sleep for less than 13 hours? And again, the answer is yes. By finding out the Z-score and using the Z-score table. Okay, so this is the second part that will help us, and because this gives us the area to the left of a particular Z value as shown below. Okay, so if we know the Z-score here, then we can figure out this area, okay, which is the probability. Here it says, remember the area under the curve represents the probability. Okay, so now this, I'm going to show you how the Z-score table works. So this, I believe, is also on Teams, so please download it, I guess. This is the standard normal distribution table, Z-score table. So it's actually quite easy to understand. It's just a table like this. So here's the Z-score. If you know the Z-score for a particular value is, let's say, negative 2.95, then you just go to this table. Here's negative 2.9, and these are the 100th place, so negative 295 will be right here. So the area under the curve to the left of negative 295 is 0.0016. Okay, so what I meant was this. Okay, so let's say we have, so negative 2. So if this is mean, that's 0, right? Negative 1, negative 2, negative 3, negative 295 is somewhere here, then we are saying, okay, negative 295, we are saying this area right here is, what was it again? 0.0016. So, or convert to percentage, this is 0.16%. Okay, so not very likely. Okay, so that's how this table works. You can see these are negative z-scores. We can move down to get positive z-scores. Keep moving, keep moving. You can see these will be positive z-scores. But we are, again, this table shows you the area under the curve for less than that particular z-score. Okay, so here's the key, right? It's the probability that the z-score is less than whatever z-score that you decided to use. Okay, so let's go back to our handout here. Okay. So going back to example 2e, what is the percentage of the day that an infant slept for less than 13 hours? So remember, I think we calculated the z-score. I can't remember. I think it was 0.5. The z-score for, that's right, the z-score for 13 is 0.5. So we are looking at an infant sleeps for less than 13 hours. So we're looking at the probability less than 0.5, right? That was the z-score. The z-score for 13 was 0.5. So we're looking for, so basically we're looking for this. Here's 0, here's 1, and 0.5 is here. We're looking for this area, and that's 0.5, which is 13 hours. Okay, so we go to the table, and we go find out where 0.5 is. Move down, 0.5 is right here. So 0.5, and the 100th decimal place is 0, so we're looking at 0.6915. Okay, so let's go back. The probability is 0.6915. So 69% of the day, the infant will actually sleep for less than 13 hours. Okay. All right. So then we can answer the question, right? That answer the question. So let's look at example number 5. Okay, so we are going to look at the probability that z is less than 1.54. Okay, so I will do this. You know what? Why don't you practice it? Okay, I'll do part B and C, and you can practice this one. Okay, so hopefully you find the answer here. 1.54 is right here. 1.5, 100 decimal place is 0.04, so it's right here, 0.9382. Okay, so this should be 0.9382. Okay, part B, it's a little bit different because now we're looking at greater than. Okay, so but what you do is this. You do the same thing. Okay, so here, let's say that's 2.15. We're looking for this. Okay, the table only shows to the left of that. So again, the table, what the table give us is this part. But recall, the area under the curve is 1. So what we can do is we can go 1 minus the probability the z-score is going to be less than 2.15, right? They are equivalent. You minus this area from 1 will actually give you the red piece, right? Will give you the rest of it. So what you can do then, I guess, is we go to the table, 2.15, just a little bit underneath, 2.1, okay, that's 2.10, 1, 2, 3, 4, 5, so this one right here. 0.9842. Okay, that's 2.15. 9842. So this is going to be 1 minus 0.9842, which is going to be 0.0158. Okay. Okay. The last one. So we're looking at in between. So negative 1.21 somewhere here. 2.34 somewhere here. So we're looking for this area. Okay, I'll pause the video. You think about it. Okay, hopefully you got it. If you didn't, that's okay. So what you can do is you can actually find this entire area right here. Right? So anything less than 2.34, and then just take this portion away. Okay, well they look the same now. Okay, you take that portion away, then you get, the rest of it. So what you need to do is to find what's left of 2.34 minus what's left of negative 1.21. Okay, so we can check to the left of 2.34, that's right here, 0.9904. So 0.9904 minus to the left of negative 1.21. Negative 1.21 is right here, 0.1131. 0.1131. 0.1131. Okay, now you can subtract them and get your answer. 0.9904 minus 0.1131. This is 0.8773. Okay, so that would be the area that we're interested in. Okay, that's this piece right here. Okay, now we're gonna go backwards and then, find out the Z-score, I guess, because now I give you the area. Now you find the Z-score. So here it gives you in percentage. So what you need to do is convert this into decimal. So 1762. 62, not 66. So we're looking for the Z-score that will give us the area of 0.1762. Okay, so we go to the table. We look for that decimal place, that decimal 0.1762. 1762 is right, where are you? 1762 is right here. Okay, so anything to the left of this Z-score will actually give you the area of 0.1762. So we just need to find out the decimal place for that one. That's negative 0.990919293. Okay, so the Z-score is negative 0.93. So Z-score is negative 0.93. Right? Oh, sure, I forgot. Yes, negative 0.93. Okay. For part B, I'll do this one as well. So this gives you what's on the right. Again, if you convert this into decimal, this is 0.1492. So to the right is 0.1492. That means to the left, that this portion is going to be 1 minus 0.1492. So if you put this into a calculator, I believe this is 0.8508. Okay, so then what we do is we again go to the table, find out where 0.8508 is. Okay, we know it's going to be more than 0, so we guess we can move down. 0. What was it again? I can't remember. 8502. 8502. Where are you? Oh, 08. That's right here. 8508. So this is 1.0. 1, 2, 3, 4. 1.04. Okay. 1.04. Okay, because that's this portion. Okay, I will pause the video. You try part C and part D. Good luck. Okay, for part C, the trick here is that you need, it's symmetrical, so that means half, right? This portion is exactly 0.5, right? Therefore, all together, you just need to add them together. So this is 0.7580. So then you go to the table, find out where 7580 is. 7580, where are you? 7580 is right here. So 0.7, exactly 0.7. So the Z-score is 0.7, right? Oh man, I forgot. Yes, 0.7. Okay, part D, similarly, okay, you can use the same fact that half of the curve is going to be 0.5. The area is going to be 0.5. That means if you combine these two together, okay, so that means adding these two together, this is, what is this? 0.21, 0.2145, 2145 plus 0.1293. This is 0.3438. Okay, so this entire portion is 0.3438. That means this is going to be 0.5 minus that, right? Because that's the rest of the 0.5. That's 0.1562. So then to the left of this Z-score, is 0.1562. So then we look for that. Where are we here? 0.1562. I guess that's the negative portion now. Okay, so we're gonna move back. point, I forgot again, 1562, 1562, where are you? 1562, 1562, right here, negative 1.1. Okay, so we know the z-score right here is negative 1.1. Now, here, because it's in between, right? So we need to find out what this z-score is as well. Now, we just figure out the empty portion here, and we also know that's 0.2145. Therefore, this entire portion is going to be 0.1562 plus 0.2145. Or, I mean, you could just go 0.5 minus 0.1293. Same thing, okay? Same thing. More than one way of doing things. Always good to have multiple methods. The 0.3707. So then we go to the table, find out where that number is. 3707. not quite. 3707 is right here. That's negative 0. Okay, that's 1, 2, 3. 0.33. Negative 0.33. So we're looking at the probability that the z-score is between negative 1.1 and 0.33. I guess I should probably roll it like this. This one we're looking at z-score between 0 and what was the z-score? 0.7. For this one, we're looking at the z-score, or the I shouldn't say z-score here. We're looking for we found the z-score in this case negative 0.93, but we're looking at the area less than that. So z-score has to be less than negative 0.93. And this one is going to be the probability that the z-score is greater than 1.04. And that is 14.92%. Okay, so actually quite a bit of stuff. If you have any questions, let me know. Some parts you might need to rewatch it. Okay, it does take some time to get all these information to sink in your brain, I guess. Okay, good luck with your assignment. Bye.